Hi, my name is Avi Nabel, and welcome to my Physics 1 Lab 2 Projectile Motion. To get things started, here's a little table of contents. This is what I will be covering throughout this lab presentation. So to start off our introduction, the purpose of this lab was to compare a projectile's actual motion to its calculated motion. So to do this, first we recorded a projectile's motion through the air. Then we had to use trackers to find its exact position throughout the video. Then we created two computational models, one with drag and one without. And lastly, we compared our findings. So getting into the principles used in this lab, we have Newton's momentum principle, the force of gravity, and the drag force. Newton's momentum principle states that F net is equal to the change in momentum over the change in time. The force of gravity is equal to negative mass times acceleration due to gravity, and drag force is equal to negative b times the magnitude of velocity squared. An important note, if there is no drag, then the net force is equal to the force of gravity, at least in this scenario. Now, our procedures. First, I recorded the object and put it into tracker. And for the object, I used a ball of paper and I threw it up. Then, I analyzed its position frame by frame. Then, using my findings, I created two computational models. One accounted for drag and one did not account for drag. Then, I compared the results between them. So here is my tracker video. And we can see that the paper ball was thrown with a parabolic arc, just like you would expect of a projectile. Now, my initial findings from tracker, the initial velocity of the object was 1.957 and 2.442 meters per second. The initial position was at 0, and the object was in the air for 0.55 seconds. And then lastly, the mass of the ball was 0.01 kilograms, but that was something we measured before. That is not something I found in tracker. And then after tracker, I created two computational models using GlowScript and using the provided starter code. So we can see up here, I set the ball's mass to the mass that I had measured. I set the velocity equal to the initial velocity that I found in tracker. I set delta t equal to 1 over 60 because my video was 60 frames per second. Here I set the drag coefficient to 0 because this was the model without drag. And then lastly, I set up the force equation. It utilized the gravity and drag variables, but because drag was 0, the only force acting on the ball in this computational model was gravity. And then I made a second computational model with all the same information except for the fact that the drag coefficient was no longer 0. This meant that drag is now accounted for in the net force, just like in the real world. Now getting into my comparison a little bit, we can see this is a graph of the x position versus the y position. And we can see in the blue, that is my actual findings from tracker, and then the orange is my computational model without drag, and my gray is my computational model with drag. So we can see that there is some discrepancy between my findings, and I'll get into that now. So here are some possible errors. There are a few human errors that could have occurred. It is possible that we measured the mass of the ball wrong, so then the computational models would be off. It is possible that I made a typo in my code somewhere and I didn't catch it. It is also possible that I used tracker incorrectly and did not place my markers in the correct position. It is also possible that there were other forces acting upon the object, such as maybe someone had a fan on and it was blowing air, and also the ball might not have been thrown perfectly in 2D. Now, getting into further questions, What does it mean? Terminal velocity is when the force of gravity acting on an object is equal to the force of drag / air resistance on it, meaning it no longer accelerates. The model without drag does not predict this, and the model with drag would predict this, but our ball was not in the air long enough to reach terminal velocity. And what if it was thrown straight up? Well, then it would take the same amount of time to reach the floor, as the only acceleration is caused by gravity, and we know that gravity is only in the y direction, so it would take the same amount of time. Thank you.